Hi, this is Math 1350, and this video is over section 1.2. We're going to start looking at functions and their graphs. Okay, and it's really kind of important to understand certain functions have certain types of graphs, and then we look at how they change as the function change. And so there's key elements that we'll look at, as well as whether or not a graph shows a function's a function or a function's a relation. So a function is a rule that assigns each element in a domain X, or a set of elements, to exactly another set of elements. Okay, so think of this as a set of all values that can go in for X. Okay, and so that's the domain of X. The function assigns that, or transpose that to another function or another set of elements we call Y. So that's our range. Okay, so domain is the set of possible values for X, and range is the set of values that we will get out for Y. Okay, and a function will assign one value to another value in Y. And there's possible that a second value can go to the same value, but that is not always the case. And so you may have another value that just goes to another random value of Y. Okay. What's not allowed is for one value in X to have two possible values in Y. That's not allowed. So the red line there can't exist within a function. That makes it an operation, or a relation. Right, so domain is a set of all possible X values. We call these the independent variables. That's what we usually plug in to see what we get out. So for instance, if it's cost over time, we plug in a certain amount of time, and then we look at what the cost would be. Or profit over a certain amount of time, we again look at a certain amount of time, and the cost would be. Or maybe it's profit per number of items being sold. We look at how many items are sold, and then what the profit would be from that. All right, and so the elements in the set for Y is the range, or the dependent variables. What can we get out? What's the highest amount we can get out? What's the lowest amount we can get out? You know, are there certain values we wouldn't be able to get out? A relation is an equation that is not a function. And so common relation is going to be a circle. And so for a certain value of X, you could have multiple values of Y. Okay, and relations are very common in like geometry, because you know, when you graph certain things, there's different points to it. All right. Relations are allowed, it's just they're not functions. Now, function notation, instead of having Y equals, you know, some value A X plus B, we turn the Y into f of X, meaning it is a function, and that f represents the name. So generally we use f or g or h, and then, you know, if we're doing some specific like cost, we may use c to represent cost. And then the parentheses of X, that doesn't mean multiply, that just means that value for that you're going to plug in for X, that's what you plug into the equation. All right, so let's say we have f of X equals x squared plus 2x plus 3, and we want to find f of -1. So we plug -1 into the equation. So -1 squared plus 2 times -1 plus 3. So -1 squared is 1. Then you get -2 plus 3. And so you have 2. Okay. We can plug in expressions. So if we plug in x plus 2 into f, we get x plus 2 squared plus 2 times x plus 2 plus 3. Or we can plug in -x, and we get negative x squared plus 2 times negative x plus 3. Okay, and then we would want to simplify each of these. So when we simplify the top of the second one, let's see, we get 4x plus 4 plus 2x plus 4 plus 3. It's going to be x squared plus 6x plus 11. And then the third one, negative x squared is x squared minus 2x plus 3. And you just simplify it down as far as we can go. Okay. Next function, g of r equals square root of 25 minus r minus 6. We can plug in 16 for 25. Oh, not for 25, for r. And so we get square root 25 minus 16 minus 6. Now that 6 is not underneath that square root. So then we simplify this, we get square root 9 minus 6. And then that's going to be 3 minus 6, which would be negative 3. And we can do the same thing for g of negative 24. We get square root of 25 minus a negative 24. This is where parentheses are so important. Now this minus a negative 24 means we're going to add 24, not subtract. You know, two totally different answers if we do the wrong thing. And so we get square root of 49 minus 6, which is 7 minus 6, which is 1. And then similarly, we can plug in whole expressions. 25 minus 2x minus 6. We get square root of 25 minus 25 plus 2x minus 6, which is square root of 2x minus 6. Okay, and you don't always get numbers out in algebra. Sometimes you just get expressions out, you know, and you simplify expressions and you make it easier to plug into other devices to graph them. And so equations is just one representation of a function. There's other ways you can represent. So we're going to go through a couple of different ways of representing this. So the cost of a mechanic is $50 per hour plus $100 for initial inspection. That's a verbal way of representing it, just writing it out in sentence form. We can turn that into a math problem. Cost, we'll go C of x, where x is equal to the number of hours that the mechanic works. C of x equals 50 times x, so $50 per every hour, so 50 times how many hours, plus 100. And there's your equation. So second way of expressing a function. Third way is, we'll do the graph later. Third way is the table. So we can make a table of values. Now, sometimes how you make a table depends on the physical situation. Sometimes it depends on what the graph looks like, and you want to make sure you get certain features. For this, we have a certain situation where negative values do not matter, but 0 does. Now, you want to know, what's the cost initially if you just come in and they don't do any work, but they look over the car real quick. And then we can go by hours, 1, 2, 3, 4, and 5. And then we can plug each of these into the equation. So we'll have C of 0, C of 1, C of 2, C of 3, C of 4, and C of 5. And so C of 0 is just 100. C of 1, you plug 1 into 50, or into x, so you get 1 times 50 is 150. 2, you do 2 times 50 and get 100, so you get 200. 3 is 150 plus 100 is 250. 4 is 200 plus 100, so it's 300, and then 350. Okay, and then we can graph this. And so all values are positive, so we'll just graph the first quadrant. So 0, 1, 2, 3, 4, 5. And we'll count by 50 here. 50, 100, 150, 200, 250, 300, 350. and then we plot points. 0, 100 is your initial. It costs $100 for them to look at the car. 1 and 150. 2 and 200. 3 and 250. 4 and 300. 5 and 550. And assuming, let's say they take it down to the exact minute or something like that, we can draw a line through it and show that that price is increasing every hour they work on it. Okay. Now the example, the height of an object is given by the following function. H of t equals 100 minus 16t squared. So in words, I would say it like this. An object is falling from an initial height of 100 feet. Okay. The reason I know it's feet is because the 16 here. Gravity is pulling the object down. Gravity is 32 feet per second, but within the equation and this will be dealing with calculus, but we end up having to divide that by 2, and so that's where we get the 16 from. Okay, so gravity is pulling it down. The formula H of t represents the path of the object as it falls. Okay, one thing I did not include, but that is true with this, is it's dropped. A dropped object, not one that was thrown down. And I know that because of what I don't see in the equation there. All right, and so that's how we, how we look at an equation. If we know a little bit about it, there's certain things in the equation that we can figure out for the actual scenario. All right. So with this, we're going to start the height at 100, and so how far we would take it, well, it's falling and eventually it's going to hit the ground. So height being 100 is the first point, and then hitting the ground is also a very important point, but we're going to want other points as well from it. But that helps determine the domain and range. So the range of the function, the range of the height, is going to go from 0 to 100. I know it starts at 100 and goes down to 0 in the situation, but we always write it range from 0 to 100 in number order. And then the domain then is the time, starting at 0 to the time that it hits, and so that's something we'll have to find out. Okay, and so to find when this time hits, we can set this equals 0. So we get 100 minus, equal to 16t squared. 100 over 16 equals t squared. So take the square root, you get t is equal to 10 over 4, which is 2.5. So that's your domain. And then we look at the graph of this. So spread this out so we can see it better. 1, 2, 3. That's your time, and then 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, so now we can graph some points. Right, first point is 0, 100. Last point is 2.50. Right now, it's not going to be a straight line. That's why we got to graph some other points here. All right, and so we want to pick points in between, in between 0 and 2.5. So obviously we're going to pick 1 and 2. You can also pick 1/2 and 1.5. All right, so let's just get some of the points here. So 100 minus 16 times 1/2 squared is 100 minus 16 times 1/4, which is going to be 100 minus 16 divided by 4 is 4. It'll be 96. So this is 96. So after a half, it goes down to 96, which we can show right there. Then we do 100 minus 16 times 1 squared, which is going to be 100 minus 16, which is 84. So at 1, it's down to 84. Then we do 100 minus 16. 1.5 is going to be 3/2 squared. Switch into a fraction because we're squaring and it'll be a lot easier to do this. So that'll be 100 minus 16, 9/8 That should be minus sign. 100 minus 4 times 9, which is 36. So 100 minus 36, which is 64. And then last one with 2. 100 minus 16 2 squared will be 100 minus 16 times 4, which is 100 minus 64, which is 36. Right. So we can see it doesn't have a straight line, it's more of a curve. And it looks like that. Break these apart so you can see what we did where. Right. Now, this equation is a quadratic. It has a t squared as the power, and that's its highest power. So having that curve is important to understand that that's part of it being a quadratic. So this is a part of a quadratic. Okay. Functions have specific graphs of what they look like. Right? Linear functions, straight lines. So if it's constant, so if, like, let's say m is 0, so m equals 0 here, then you get f of x equals b, so everywhere on x it's a straight line, and so that's how you get this graph. And it could be a positive line, or it could be one that's going negative. But those are all linear graphs. Power functions, things that have x raised to a power, they have certain types of graphs. If it's an even power, so this is maybe hard to see, 2, this one's 4, it's going to look like a u or possibly a w. If there's more terms to this and it's more of a polynomial. Alright, as the even power increases though, we can see that it gets a lot more horizontal here at the center. Odd powers look like a snake, so this is 3 and this is 5. And so it's more like a snake. And again, when the powers get higher, this area gets more evened out. Alright, so we're going to look at some of these. Let me bring in Desmos. So we're going to start with f of x equaling 4 minus 2x, and we see it's a straight line. And it's a downward line, and specifically it goes through the point, and we can click on it, 0, 4. So this is 4, and so it goes through that point. Has a slope that is a -2. We know it's downward, so it has to be negative. And then it also goes through the point 2, 0. Important features of these graphs, so the x-intercept, and the y-intercept. Okay. And then put in important feature about this equation is that slope. We can look at another linear one. In this one we're going to restrict the domain so it's not the whole graph. We'll just do this from actually 1, 2, 3, -3 to 3. Right, so to do this on Desmos, x plus 3, we need to put in braces. So we hit brace, -3 less than equal to x less than equal to 3, and close the brace. They all close automatically. Okay, yeah, we can see it's graphed. And here we can see that the y-intercept is 0, 3. And so it's also a downwards. The x-intercept is 3, 0. So we have a graph like this. And it stops at the endpoints, the other endpoint being -3, 6. If again, it's a horizontal line because it's a linear function. Okay. Power functions. So let's get these. Okay, so x squared minus 4. And so we see it's a quadratic. Important features on here. Again, x-intercepts and y-intercept. 2, 0, -2, 0. y-intercept being 0, -4. Which is also your vertex, right? This isn't always the case that the vertex is the same as the y-intercept. In this case, it is. Right. Now, this one, for a lot of these graphs, the linear graphs and the power graphs, the domain's easy. It's all real numbers. But for the range, and for this one, the range here, you'll see is from -4 to infinity. Okay, the range can be different. The domain and range for the linear functions, well, the domain here was restricted. So that was the only one that didn't have a real numbers domain. We can say the domain is all real numbers for both for that one, and just -3 to 3 for this one. The range is all real numbers, and then from here it goes from 0 to 6, following the fact that restricted domain restricted the range as well. This one, the domain was again all real numbers. Okay, and the cubic one, it has that snake-like look to it. So it crosses the y-intercept at 0, 1, x-intercept at -0.4534. So I'm just going to put a point there. And then it has that snake curve to it. Okay, domain here, all real numbers. Range, all real numbers. So without a restricted domain, the cubic always has the same domain and range, and they're both all real numbers. Alright, so root functions, it depends on the type of root. If it's even root, you only have positive sides, because if you had the other side, it actually ends up not being a function. But this first one's a square root, then a cubic root, then a fourth root. And notice the fourth root, it just has it be go a little bit more vertical before it goes over. And then the fifth root, and the fifth and the third, they have both sides for the fact that negative values you do get out with fifth roots. Receptacles, they look like this. A lot of times they'll have asymptotes, not always, but they will. So the 1/x has asymptotes at y = 0 and x = 0, so at the y and x axis, and the graph doesn't cross it. The 1/x², notice basically the bottom portion of the 1/x is squared, and so every negative values become positive. So it has the same asymptotes, but it's just in different quadrants. The absolute value graph looks like a V. It's really a piece function that is made up of y = -x and y = x. And the greatest integer function is a step function, and I'll get into that one towards the end. Right, so let's graph square root of x - 2. And so we can see it starts at 2, 0, and it has that upwards curve to it. 2 dot tier. There's an upward curve to it, and it's one of those functions that, you know, starts out kind of quickly, but then it starts to really level off real quickly, and so it does not get to high values until you get to really big numbers. And so the domain here we can put in 2, but we have to put everything above it, and the range, you'll get 0 out or anything positive. The next one, let's put in the cube root. I'll just do x. Actually, it'll be negative x, so I'm going to do parentheses negative x raised to the 1/3 power. And that gives us the cube root. Okay, so it comes down. Okay, its domain is all real numbers, and its range is also all real numbers. Okay. It doesn't go that high quickly, but it does go as high as it needs to. The square roots, I mean, the whole operation is kind of reducing the value of the function, or what's in the function, or what's in the root, and so these numbers are always smaller than they would be if there was no root there. We can look at some rational functions. This one gives a domain restriction, but when we graph it, we're going to see that it happens sooner than what the actual restriction is. So let me get it graphed. So x minus 3 divided by 2x. Actually, maybe this isn't the one I was thinking of. And so do the braces. Negative 5 less than x less than positive 5. Right. Yeah, this wasn't the one I was thinking of. Alright, so here we have an asymptote, and we actually have a horizontal and a vertical. The horizontal is at y equals 0, and the vertical is at x equals 0. Eventually we'll get into how you find these from the equation themselves. It's not too hard. You know, we can see that if we plug in 0 for x, we're going to be dividing by 0. So that's why there's a vertical asymptote there at y equals 0. And then if we plug in, or if we look at ways of finding the horizontal asymptote, we'll find out that's why. The fact that the x, the numerator, is 1 degree less, actually it's the same as the denominator. Well, that should change something here. Oh yeah, so now that I look at that, the asymptote, it's hard to see in the graph, the asymptote is not at y equals 0. It seems like it could be, but it's not. It's at y equals 1. I'll zoom in some here. Make this dotted. There is a way to tell from the graph, and the fact that they have the same degree means that you look at the coefficients from the x and divide them. So it's 1/2. So let me change that. Y equals 1/2. So we can see it, the cost is the y-axis, but we can see that it's coming up to that y equals 1/2 point. It's not going to cross it. Same thing down here. It's coming down to that y equals 1/2 point. Right, so it has a y-intercept or x-intercept, which is 3, 0. That helps in drawing this. Oops. So it looks like this, and then it looks like this, and it stops where this is 5. Alright, so we can do the next one. I made that one kind of big too, so I'm not going to have a whole lot of room here. Here, this one will have y equals 0 as an x-intercept. Or not intercept, sorry, as an asymptote. One divided by 2x squared. And so we see this one does keep extending because there's no restriction that was put in on the domain that's not supposed to be there. But we see that there's an asymptote at our y-axis and at our x-axis. So you can look at the absolute value function. This one's kind of interesting because most of these are v's, but this one actually ends up not being a v. And it's because there's other things going on, including the fact, well, mainly the fact that we're subtracting x. So it's going to be interesting what it looks like. So absolute value of x minus x, and so it looks like it's only a part of a v. Right, so 0, 0 goes through. But then no matter what you put in for x, you're subtracting that value. So it ends up being 0 all the way in the positive domain. Okay, the reason it's not in the negative domain is, let's look at one. If we did, let's say, h of -5, then we have absolute value of -5 minus a -5, which is going to be 5 plus 5, which is 10. So it's actually increasing that line on the negative side. Domain is all real numbers. Range is 0 to infinity. Okay. So now let's get into some piecewise functions. These are functions put together by putting multiple equations together, and each equation is restricted in such a way that there's no overlap. So for instance, if you look, you have x less than -1, and so it includes everything that's less than -1 but not -1, and then the other section includes everything above -1, including -1. And so if we look at these, we see that both graphs here are linear. Bottom one has a negative slope. Top one has a positive slope. It's going to increase as x increases, and the other one would decrease as x increases. All right, now put in some points here. I'll graph this first by hand, and then we'll plot it on Desmos. And the reason I'm doing both is because to plot this on Desmos, it takes a couple things that we need to do, and some of the stuff we need to do by hand. So first, we need to look at both of these equations at -1. So even though the top one doesn't include -1, we still want to look at it at -1. So we'll have 2 -1 plus 3, which that'd be -2 plus 3 is positive 1. And then we'll have 3 minus a -1, which is 3 plus 1, which is 4. Alright, now the bottom one's included. So at -1, you have 4. So it's included, we put a solid circle. The top one is not included. So at -1 you have 1, but it's not supposed to be there, so we'll put an open circle. Right, but it is an endpoint, and that's why we want to actually graph it, so we know that's where it's going to stop. Right. Next thing is we want to look at these equations, and we can do this one at a time. First we're going to look at the top equation. If x is 0, it crosses the y-axis, so we get 3. So that's the next point. And then we want to do one more point, maybe when x is 1. We get, oh, I'm doing the top one. Okay, yeah, when x is 1, we get 5. So here's this one. And so we get a line here. Oh, I'm doing the top one. I'm doing the wrong side of this. All right, let me go back. Top one starts from -1. All the things we plug in have to be less than -1. So we'll have to look at -2. So if we put in -2 plus 3, we get -4 plus 3, it would be -1. So -2 drops it down to -1. It's going to be kind of right on that too. And so we can graph this going down. Right. Then the bottom one, it crosses at 0, 3. So that's the second point. So we can draw this one down. That's your piecewise graph. Alright, so what we're going to do on here is we're going to do two equations, f of x and g of x, since there's two parts to this. And the reason I'm doing two equations, so if we need to use a table, we can. So first one we'll just plug in 2x plus 3. But notice that it does the whole line. You know, it doesn't just stop. So we gotta tell it when to stop. So brace x less than -1. And so it tells it to stop. And it's only on that side. And then the bottom one, 3 minus x. And this is going to be when x is greater than or equal to 1. To -1. And so it gets that portion of it. Okay. So I'm not getting any of my tablets not working for some reason. There we go. Okay. So basically what we have, it crosses at 303 and it crosses here at point negative 1.50, but we see negative 2. Try and get it on here. I can't get it. All right, anyways, I'll plug in these points. So we're going to plug in some of the points we did. So negative 2, comma, negative 1. So at that point, we also did negative 1, comma, 4. So we get that point. And then we did 0, comma 3. So we get that point. And then one really important point here, negative 1, comma 1. And that one we're going to make a hole. Okay, so I'm going to turn some of these color of the graph. Right. And so now we can see those features on the graph, on a piecewise graph. Alright, so we'll do the next one. We're just going to graph it on here and then I'll point out certain points. So we'll do 2x minus x squared. And it's going to be when let x is greater than 1. And then we'll do x minus 1 cubed. And it's going to be when x is less than or equal to 1. And then the points we want to find on here. Alright, so 1 is included in the bottom equation. So instead of plotting these points just by plugging them in, we can do a table. And I can put this at f of x. And 1 over we'll do g of x. And then this has to be, you have to make that x. Okay, now we can see those. And I'm going to match up the colors here. So g of x is going to be purple. F of x is going to be red. And so the main point we want to put in is 1. We see it's undefined at f of x, but it gives us a value of 0 at 1. So that gives you your solid graph. So how we get the open point? Well, we do have to find that. So f of 1 is 2, 1 minus 1 squared, 2 minus 1, which is 1. Okay, and this is for the whole. So we'll put in that point. 1, 1. And then make it a whole. Okay. And then we can plug in some other points just to get points on the graph too. And we can do 0. And notice it chooses which one it goes to depending on the functions. So if we do negative 1, it's going to go to the g of x function. If we do 5, it's going to go, let me do one on the graph or in the screen. 3, it's going to go to the f of x function. Right, the last thing in this is the vertical line test. This is the easiest way to tell if a function's a function. It's very simple. You just look at if you can draw a vertical line anywhere on the graph and it crosses more than one point. Now, these graphs, like this quadratic, this is always going to the right even when it gets super vertical, and this side's always going to the left even when it gets super vertical. So no vertical line will cross 2 points. So this is a function. Okay. Opposite of this is a circle. Draw a line through, crosses points here and here. Then it's a relation. Okay. Equation-wise, if you know the type of equation you have, so you have a quadratic, you can automatically say, okay, well, I know that's a function. And that's why recognizing the symbol. So if you have a cubic graph, x cubed, you know that's a function. If you have a rational graph, you know that's a function. Okay. So when the ones you don't know are the ones that when you graph them, you see something where you can easily say, okay, well, if I draw a vertical line crosses 2 points, it's not a function. For instance, this x squared plus y squared equals 4. Whenever you see the y squared, that also is going to indicate you're not dealing with a function here. Okay, we'll get more into functions and relations as we get into other topics like inverses. Alright, so next video is going to be on 1.3. I'll see you then. Bye.